Hi, we are live from Johns Hopkins Presents here on Homewood campus. Today we are at the JHU Design Day for Engineering, and I'm here with Mary Beth Regan. We are here live in Hodson, and we're so glad you're tuning in. We're going to go ahead and show you all the great design projects that students have been working on all year and find out a little bit more about this great event. So we're going to start off with Mary Beth. And can you tell us more about what Design Day means for the engineering students?
Yeah, definitely. So here on Homewood campus, today we have about 100 student projects, graduate and undergraduate students from all different disciplines, and they're showing everything from a new way to press wood to make guitars to a new medical device to help healthcare workers better find veins. So our students are working all year. They're working with clinical sponsors, industry sponsors, advocacy groups, government agencies, and they almost get an open book. When given a problem, they can come up with solutions.
That's fantastic. So as we said, we are live streaming here from the Design Day, and we're going to be lucky enough to be taken around and actually show you some of the unique projects that students are working on that you're talking about. If anyone has any comments, please chime in and we can try to answer them live on air. Also share this video with friends and we'll get more people involved in this awesome project. So thank you so much for tuning in, and we're going to go ahead and move to our first student. So this is Ukrit.
Hi, how's it
How
going?
are you doing?
I'm great, thank you. How
I'll
are you?
stand over here because we want
Sounds
to see your
good.
project. But what are you working on?
So we are a design team working with the Hopkins Hospital on developing a new way for bone marrow aspiration. So bone marrow aspiration is one of the most expensive and most painful procedures done in the hospitals, with the evaluation of around $64 million per year. And looking at how the established procedure is going, we found some fundamental issues with the current procedure. So our team developed a device that couples with the current system that will streamline the process and minimize the contamination issues in the current procedure. So here we have a prototype of a project where conventionally the extraction process is a simple needle syringe suction collection process where 11 syringes are filled individually and then transferred. So what we did here is modify the current workflow by adding a valve system that turns this procedure into like a bike pump kind of mechanism, as you can see here from the prototype. So the system now is a basic bike pump where you draw in the bone marrow and then expel it out, where the valve would redirect the flow of bone marrow from the syringe to the bag when the collection starts from the container. And this project we've been working hard with the hospital this whole year, and we hope to continue developing the project and work with the hospital for clinical and market translation. And
So how long has this whole process taken from start to finish?
It's been a wonderful academic year, and we plan to continue it. And hopefully by the next year, we really want to place our product in the market.
So how many students work on this project?
Yes, this design team has 8 people, 3 seniors and 5 juniors, and it's all undergraduates in the material science and engineering department.
Fantastic.
Awesome.
Well, this is really cool. I'm loving this demonstration. How has it been going today? Have you been just showing off all the different stages of the process?
I mean, Design Day's been amazing. There's so many cool posters and projects going on, and definitely some of the things that I've never thought about, and I was definitely super impressed and surprised by it. And also the feedback we've gotten so far this today has been amazing, and it's definitely helping us with the development and the innovation of the project.
Great. Well, thank you so much. This is a really great project. So we'll be moving on to a couple more projects. This has been fantastic from Ukrit. So, Mary Beth, if you would help us, we're going to go ahead and move through some more projects like we talked about. So the first one.
I'm going to introduce you to some folks right over here.
As we said, if you have any questions, please continue to comment them and we'll try to answer them as we speak to each of the students. So the first group we're stopping at. Hi.
Elise Lance.
Okay, can you tell us what is this project and what is your group been working on all semester?
Okay, so we've been working with Smith guitars and basically optimizing their manufacturing situation. So what's really cool about this company is there's so much integrity and soul in their brand. Everything is touched by a human. They're real craftsmen and artisans who make these guitars, but they're really doing really well. So they need more efficient processes to keep up with their current demand. So basically we spent the past year trying to figure out how to best improve based on like prototyping and trying to figure out monetarily what would make the most sense. So we really settled on 2 different projects, which are the body pressing right here, which is the front of the top of the guitar and the structural back, and then also the scarf joint, which is the top part here, which is where the tuning strings are, the headstock, and then to the neck of the guitar. And then through destructive testing, we figured out like basically how to make it faster. So we did radio frequency gluing, which is basically using microwaves to cure the glue faster, allowing to make it a single stream process. Because right now they use basically time and pressure to make the glue lines, and it's not very efficient. It also can lead to a lot of errors, which is really bad considering how expensive and nice the wood that they're using is.
You said destructive testing. What does that look like?
So, I'll have Tom explain it because he did a lot of it. It's really cool.
Destructive testing? Okay, so for destructive testing, we basically take... Sorry, can I grab that one? You take the scarf and you're going to put it so that the angle is facing convex up, and we just apply a load directly to this top part here until we get failure, and you'll see them splinter just like here. Your goal is to have the splintering take place in the wood and not on the glue line. This is the glue line here, and that just proves that the glue line is stronger than the wood itself, so our part is holding up to our strengths.
Great, that's awesome. It looks like a lot of fun to the testing. How long did it take you to get to the final project where you have now? The sort of
a whole year. No, because the first whole semester we did was basically just trying to figure out what made the most sense. And a lot of it was like time studies, optimization of like money, like payback period, that sort of thing. Also figuring out like what is actually a bottleneck in their current process. And that's how we landed on these 2 projects. And it also really helped that both of them were similar enough that we could use a lot of the same like ideas, even though they were different scales, to complete both of them.
And you said you did collaborate with a company, obviously. What did that look like in terms of meeting professionals and working with another team?
So the company's great. Bill Ortell, who's the head of manufacturing engineering, is amazing. He's been there every step of the way, like on the phone with us. We usually go down there at least once every 2 weeks, if not more. We've met Smith himself, who is the owner of the company, and he's like the brain behind all of this, and he's really excited about our project. We've worked with everybody from techs to like design people, like very involved with their team as well, which I think made it really cool, especially because a lot of the techs were like, you're listening to us? Like, you care about what we said? I was like, you have 30 years of experience. We're not going to like joke with you on this. So their feedback too helped us a lot with our design process to make it like feasible for them to use it.
What's the next steps after this? What happens now that you've done all this work? Where does it go from here?
So basically, right now we're in the process of implementing it into our current, into their current manufacturing process. So basically training the techs how to use it, making sure they're comfortable with it, basically figuring out a exact procedure for how to use this device because it requires tuning based on the different woods that you use. So basically that's it. It's really almost into production, and we hope that in the future they will use more of this type of design for the different gluing processes in their plant, making it faster and still maintaining the integrity of their brand.
Well, that's fantastic. Congratulations. You guys have done so much hard work, I know, so this is great. Okay, so we again are at Johns Hopkins Presents. We're live here in Hodson for the Senior Design Day for Engineering. We're talking with all the students we can about their fantastic projects. We had Mary Beth Regan on before, who's an editor for the engineering, and she was telling us all about this great day, and we're going to continue to move through. If you guys have any questions, please keep adding them, and we'll go live from here. We'll move on to the next project now. So we have
Danny.
Okay, nice to meet you. How has it been going so far, and can you tell us a little bit about your project?
Sure. So it's been going pretty great. Our project is working with the Space Telescope Science Institute, and their project is to work on the next generation of space telescopes. So you might have heard of the James Webb Space Telescope, which is the new telescope to replace Hubble that's launching next year. They're actually working on equipment for the one beyond that, past James Webb. It's called the High Definition Space Telescope. So if you take a look at our poster briefly, the goal for this is to look for life on other planets. And in order to do that, you need really precise equipment. So they're working on equipment called apodizers, which take the glare from stars and reduce it so you can actually see these planets next to their stars. However, in the data they're taking now, they're getting a lot of noise, and in order to see these faint images of these planets, you really need to be precise. So we worked on a mount for them that has 6 degrees of freedom and a piezoelectric actuator that'll compensate for all of this noise that they're getting.
Great. And how did you guys even start on this? This is obviously a great project to be working on, but what was the beginning inception of this?
So we actually started on this project just this spring, and we were talking with Nathan from Senior Design, and he mentioned his friend Remy, who he works with there, and he needed this project. It's been something that's been talked about for a while, and we're like, oh, that sounds interesting. So we met with Remy, kind of went over what his lab was like, saw his lab, talked about the project, and we all felt like it was really interesting to work on something, you know, this new telescope and all of this really hard, true science and engineering. So that's kind of how we got started, and from there it just developed into this project.
So obviously you have this great presentation, you have this example here. Can you tell us about the prototype step by step? Because maybe people won't know what all the different parts are and what you've sort of designed.
Sure, I'm actually going to hand that off to Cora to talk about the prototype.
What's your name?
Cora.
Cora. Nice to meet you. Nice to meet you. Can you tell us a little bit about this?
Yes. So it's a combination of a whole bunch of different optical stages. So this bottom one moves in the X, Y, and Z directions, with each has an adjustment screw. Then around to the front, you can adjust this screw and a back screw to move in the tip, tilt, rotation directions. And then all the way in the back, you have a clocking stage to move in the rotary direction, spinning this front piece. And then, Blaine, if you'd like to explain.
What's your name?
Blaine. Yeah, and so then this special appetizer fixture is mounted to the front here, and we have easy access to remove it. You just unscrew this, and it will be located on a lens cap right in here. And then for protection, we have this lens cap right here, so you can just put it on, and then to install it, you just simply screw it on. If I can get the threads in. But yeah. And then it's on.
There you go. Wow. Well, you guys make it look very easy, but I know this took tons and tons of work. So what has been the most challenging part of this project?
The most challenging part? That's tough. So we actually had... What? Yeah, putting it all together. So we actually, a lot of the time frame was spent developing these ideas, and with only a semester to work, we ended up only starting to manufacture and build everything in the last 2 weeks or so. So we were really crunched for time to build all these parts. A couple of the steel components you see there were hand manufactured by us. So it was really hard. It was a good experience to get all of that done really fast and make sure it all fit together properly, because you had to have very precise alignment for a lot of the components.
So you said some of these parts are hand manufactured by you guys. What does that mean for people watching?
So some of the steel, we would have a block of steel of some shape, either a cylinder or a block, and we had to put it on a mill, put it on a lathe, kind of go through, cut out parts, drill holes, get it all to line up appropriately for all of the parts that we bought for the mounts.
So is that something you do on campus? Where on campus are you working on this project?
Yeah, so there's in the Senior Design Building, which is in Wyman Park, we have a couple of small mills and lathes there, and we have the machine shop in Wyman Park. So a lot of the time in the past 2 weeks was spent in the machine shop under Wyman Park, working on the mill and lathe. Many hours. It was
great. Well, that's great to hear. You guys are working on campus on such a large applicable project. So that's a great thing to have. So we're going to go ahead and move on. Thank you so much for your guys' time. We're going to be moving on to the next senior design project. So we have...
My name's Ryan Seelig.
Okay. And can you tell us a little about this project and what you guys have been working on?
Yes, so this is the AFRL team. Our task was to build an all-terrain motorized vehicle for the Air Force. Some of our objectives were to build a device that can carry a wide range of cargo, everything from oil drums and ammunition to wounded soldiers in the battlefield at a variable speed, anywhere from the speed of a human walking to a human sprinting. And that's easy to control, and it's basically a personal ATV. And it's able to deal with the unique off-the-road terrain and be quiet for stealth missions and have a wide range of applications, really.
So how did you first settle on this project, and how have the stages worked out so far for you guys?
Well, many of us were actually already minoring in robotics, and this was one of the more heavily related robotics projects. So it appealed to most of us, and we kind of pushed each other along those lines to select this project in those terms. And then we came to this solution through various of design steps. Mainly, we started out with a different prototype, as you can see here. This prototype was meant to focus on the patient transport aspect of our objective. And we took what we learned from this and then applied it into the next design stage, which resulted in the prototype you see in the middle.
You've obviously had to collaborate. Who have you been working with to make sure this works in real life and works for the people who are intended to use it?
Yes. So in addition to the team you see here, we also had 2 junior members who are not here today who helped us along the way. We also relied heavily on our instructors as well as a few professors around campus in their areas of expertise, especially in relating to electronics and robotics. In addition, we also dealt with various subject matter experts, that we like to call them, end users, that were able to provide insight into what the Air Force or military personnel would actually want. What would they find useful? What would they not? What would, in their experience, works and what doesn't?
So what do you have here on the display today? Because you seem to have a lot of different parts. Can you walk me through each of the simple steps?
Yes. So here you see our hub motors. This is what drove our wheels. We had 6 independently driven hub motors and wheels that you see here that allowed for our device to get over the obstacles because each wheel was driven. Next, you see this yellow fabric. This is actually military grade Kevlar. It has extremely high strength to weight ratio, meaning it's very, very light and yet very, very strong. So it allows us to maximize our cargo space in here, however, keep our weight down. This is a bike part. We ended up actually buying several bikes and chopping them up to make our limbs. They're all made out of bike parts, like you can see here and there. And then, in addition, you see this is actually carbon fiber. We were experimenting with this for a while, and then for the limbs, and then ended up settling on making them out of bike parts. But we would like to emphasize that this is a big future application of our design to help strengthen our design, take it to the next level, and even further reduce the weight.
That's great. So did you work on all these materials? How did you come up with all of these? Is it something you learned in class or something you discovered along the way, or the experts' advice that sort of helped you settle on these parts?
A little bit of both, to be honest. Some of the things like bikes, for example, we've worked with in the past as mechanical engineers. We have some experience dealing with these structures, and our professor put it in terms of like, don't reinvent the wheel. Bikes are already made. They're very strong. They're very light. And so we wanted to make our jobs as easy as possible. And that's where the bikes came from. Things like carbon fiber and Kevlar, we really had no experience with, and we really relied heavily on the interactions between us and our professor, as well as research we did independently, and then a little bit of experimentation here and there.
Well, this is a fantastic project. Thank you so much for sharing. I know you guys put a lot of work in, so it's great to see you guys presenting. Again, we're at Johns Hopkins Presents. Thank you so much. And we're going to go ahead and wrap up our live stream from this section of the showing, and we're going to go ahead and move to another project over here with more students. This is Johns Hopkins Presents from the Mechanical Engineering Design Day. So we're going to go ahead and move past. Hi. Nice to see you. So what is your name, and can you go ahead and tell us a little about what your project is called?
Hi, I'm Sophia Diaz, and this is the FlexRay. I've been very fortunate to work on a team with 5 other mechanical engineers and with surgeons, interventional radiologists down at the Johns Hopkins Medical Institute. And so the FlexRay is a device in order to alleviate the weight of lead vests off of the shoulders. And so it is a, yeah.
So the original problem is to alleviate the weight, right? Can you explain how that...
This is a great image to really describe the problem. So interventional radiologists are working 6 to 8 hours a day, 5 days a week, and they're wearing these lead vests. These lead vests and skirts in total can weigh up to 20 pounds. And so you have all this weight, as well as you're bending over, you're moving around, so your spine is in compression, meaning that you can get a great amount of lower back pain. And if you look over there, my colleague and other engineer, Emily, has a FlexRay, and she's showing how you can integrate it not only to the lead vest, but easily get it on in simple steps. It's a carbon fiber and Kevlar composite and is integrated with a muscle belt for great fit and contour. So
This is the prototype itself. This is what you guys created through the design project.
yep, that's how we developed it.
And how did you sort of get this finally produced that we're standing in front of it and looking at it? What?
So it was a lot of work with all of us learning how to redistribute the weight, because the whole idea is to get the weight off the shoulders. You save the back, you save the surgeon. So that went from either distributing the weight from the shoulders to the ground or the shoulders to the waist, and we went with the waist because that's what our end users liked the most and is feasible with today's lead vests.
So you said end users. What does that mean?
So end users are anybody who uses lead vests daily, and so definitely in interventional radiology, you have the surgeons, the nurse, anesthesiologist, technician, and there are many other fields like orthopedics use a lot of radiation because it's fluoroscopy.
So did you have actual professionals testing out this equipment?
Yeah, we're very proud to say that we got 34 users into the FlexRay and lead vests down at JHMI, my bad.
Okay, great. So they're using them now down there?
Yeah, they have used it through several surgeries, and of course, they give it back, and we're performing tweaks and such, and yeah, it's a very.
So what you have? It seems like you have a lot of stages here. Can you talk me through what the different steps were?
This is the first FlexRay. This one was a proof of concept, and then moving forward, we made the second iteration. Then we realized that we weren't getting the greatest abilities of we weren't optimizing the capabilities of the material, so we had to vacuum bag them. So that's why this one's extremely rigid and extremely strong, as you can see. And then from there on in, it became what is the best method to achieve a size range, because you could go custom or you could go size ranges. So these ones, the next iterations, one was on metal molds that we did to the curvatures of people's back, and the other one was adjustable mannequins. So it's just different methods of production that came in to get that perfect.
Well, it looks so professionally done and really wonderful. So I'm so glad to hear you guys have been able to actually apply this in real life and have professionals use it. So, what was the best part of this whole experience?
I think the best part of this experience is not only getting to work with other engineers and other people who are very passionate about the project, but the learning experience and getting your hands dirty and really challenging yourself and what is taking something from concept to product.
Well, you've done a great job of identifying a problem and finding an immediate solution, so it's really great work. Thank you so much for talking to us. Okay, we're going to have one more presentation today. We've seen so many great projects. We're going to move on to the next group. Hi. So what is your name?
I'm Walter Sane.
Okay, and we're going to move in here. If we could just see your project a little. We want to see the prototype. Okay, so can you tell us about what your group is working on?
So our goal is to have this device go on a Blue Origin New Shepard propulsion module and collect micrometeorites in the upper atmosphere.
Okay, and can you tell us about what you have on display here?
So we have 4 identical capture units that will open and close at different stages of the flight to collect contaminants and to collect the micrometeorites. We have the tank is the positive pressure system, which keeps them sealed from contaminants when the units are not in use, and batteries and some electronics and such.
So how did you begin working on this project? How did your group come together and decide on this?
We applied for it, and I don't know. We did a lot of research on a previous NASA mission called Stardust, where they did a similar thing, but in space. So ours would be in the atmosphere. They left their device in space for months or years, maybe, and we used a lot of inspiration from them, such as how to hold the aerogel, which is our collection medium. It's a very light material that cushions the impact. We had a lot of information from them.
What have the challenges been in creating something as complex as this?
A lot of moving parts and debugging, and we tried to do analyses of the stresses and the vibrations, and just with so many moving parts, it's hard to get the models correct, but we use them to not necessarily get values, but to just determine areas that need improvements and fix those up. Did physical testing and compared, and we got a system that held up to all of our tests, so that's good.
Well, congrats on that. What are the applications moving forward? What are next steps for you guys and your team?
So the next step would be pass this on to another group that does much more vigorous testing for temperature control, vibrational control, and just to make sure that it would survive everything that it would see during an actual flight. So our goal was more to push forward the design, and then the next group would be the testing.
That's great. Well, you guys have done so much great work, and I know this has been a really long and drawn-out project, so we're so great to see everyone here presenting their projects for Senior Design Day. I want to thank you so much for showing us your work. We are going to go ahead and wrap up what has been a great day at the Mechanical Engineering Design here in Hodson. We've seen so many great presentations, and we're so thankful that you guys tuned in live for us here at Hopkins. Thank you very much, and we'll see you guys in the next semester.